Okay, I'm going to talk about a topic from Chapter 3, modulation bandwidth. And this is essentially another way of characterizing our fiber optic systems in terms of their frequency response. We've spoken so far about the pulse spreading, delta tau, and we've related that to our maximum bit rate as an input to the in the system, and said that the pulse spreading has to be that the bit rate is limited by the pulse spreading. We essentially said that the bit rate had to be less than 1/2 delta tau, and that gave us our rate distance product that's so important. Another way of looking at this, though, another way of asking this question is, instead of asking what is the maximum bit rate we can transmit with the system, think in terms of frequencies. Okay, so think more fundamentally in terms of the frequencies as the input to the system and what happens to them on the output. So I've got a very general diagram here showing a system which we should, for our purposes, consider as the fiber optic system, a piece of fiber, let's say. And we have as input an amplitude A and a sine wave of frequency F. So we're going to characterize this behavior of the system as a function of the frequency F. And it turns out that on the output, in general, we're going to get another sine wave of frequency F, but the amplitude of that sine wave will be frequency dependent. And we'll see that it often, sort of generically speaking, goes down with frequency. I've got a spreadsheet posted that illustrates this sort of in a direct way using what is essentially a boxcar average. What I've got here is over in the very left-hand column, I've got a time axis, and over here I've got a bunch of sine waves of different frequencies. So I've got a sine wave of frequency 0.1 here, a sine wave of frequency 0.2 in this column, 0.3, 0.4, 0.5, and then finally it jumps up to a frequency of 1 here. So the frequency is increasing as I go from left to right in these sine waves. And I've got a plot of these sine waves, but what I'm plotting is a smoothed version of each. So I'm plotting this column, for instance, for the first sine wave. And this point is taken as the average of all the neighboring points. This is sometimes called a boxcar average, and it really does mimic the effect of pulse spreading, and it really does mimic the effect on the frequency response of many systems. And so I've got the average here. The next point down is, so essentially we have a sliding average here to give the points in the column that I'm plotting. And so you can see here now in the plot that I have the original sine wave plotted on the bottom, and it has an amplitude of 1, and it's going from -1 to 1. And then subsequent sine waves with higher frequencies and the same averaging scheme being applied to them are plotted higher and higher on the graph. And you can see that as we go higher up, the frequency is increasing. That is, the period as a function of time is decreasing. But we can also see that the output amplitude decreases very markedly. And when I take the jump up to a frequency of 1, the amplitude goes down very much, and you can see the amplitude is essentially going away as I go to higher and higher frequencies. This can be understood very simply by thinking about that average, and if the point in my output is the average of a number of points in the input, as I go to higher frequencies, I'm going to be averaging over many periods in that input wave. And you can see that the average over many periods is going to go to 0 because the sine wave is centered on 0. And so that's essentially what's happening here. And so this boxcar average really does represent a pulse spreading type of phenomenon, and very generic in systems. And I've also illustrated that here in this part of the spreadsheet, where in this column I've got an impulse input. So I have zeros and then I have a 1. I have a whole bunch of zeros, then a 1. A whole bunch of zeros, then another 1. And those impulses are shown in this plot as these big spikes that go up to 1. And I implement the same boxcar average, or the same running average here, and you can see now that the output is these broadened pulses down here at the low. So their amplitude is much lower just due to the averaging, but you can see that this type of running average really does mimic the pulse spreading phenomenon. So this spreadsheet's available, and it illustrates the fact that A prime of F is typically a decreasing function of F. Okay? And what we do to characterize our systems very often is we write down what's called F3dB. And so defined as the frequency at which the output is half of the input amplitude, such that A prime evaluated at F3dB is equal to 1/2 of A. Okay, where A is the input amplitude. Okay, so this is the basic idea of the 3 dB bandwidth. You can call it the 3 dB frequency, but it's also called the 3 dB bandwidth of the system. And it's important because, as I say, it is a fundamental way of characterizing many systems, frequency response, and for our fiber optic systems, we do have a fundamental sort of pulse spreading phenomena occurring, and a good approximation is that the F3dB is approximately equal to 1/2 delta tau. Okay, that certainly is reminiscent of what we did here